let's start off with a recap of some of the essential definitions that we'll be needing. And today, I'll not give too much details on previous work or motivation, so I'll directly delve into details. So, one notion we'll be needing is min entropy of a random variable. So, this is the worst case analog of Shannon entropy, and it's defined as so this is a suitable normalization which is good, and the point is that we look at the element in the support of x where x places maximum weight, and that's the minimum uncertainty that x has. So that's the min entropy of this random variable x. So as an example, say x is uniform on a set of size 2 per k, then the min entropy of x by this definition is k. And for the purpose of this talk, whenever I say a random variable has min entropy k, you can as well as visualize it as being flat or uniform on some unknown subset, all right, of size 2 per k. We'll be dealing with n comma k sources. So that's a random variable x on n on strings of length n with min entropy at least k. All right, some related notions. So we'll be using a lot of t-wise independent distributions. On say n-bit strings. So D is a t-wise independent distribution on n-bit strings if any projection of D onto t coordinates is the distribution ut, where ut is uniform on, right? So ut is the distribution which is uniform on t-bit strings, and any projection of this distribution D onto t coordinates is the uniform distribution. So these are t-wise independent distributions. And finally, we will sometimes use the notion of statistical distance between distributions, between discrete distributions. So this denotes the statistical distance between D1 and D2, and this is defined to be half of the L1 distance of these distributions. So by D1 of x, I mean probability that D1 is equal to x, where x is in some universal set omega. All right? Okay. So these are the basic preliminaries, and now let's look at what our goal is. Our goal is to design an explicit two-source extractor. So let's define what a two-source extractor is. You have two independent n comma k sources x and y. And the goal is to come up with a function ext such that, so for any source x and any source y which are independent, the statistical distance between the output of the extractor and the uniform bit is epsilon. So the crucial thing is this extractor has to work for any two independent sources, because given two independent sources, it's easy to come up with a function. Right? So equivalently, this can also be interpreted as probability that the extractor is almost unbiased. All right, so this is our goal, to design such an explicit extractor in time poly n. All right, and so what was previously known? So let me quickly mention the previous work. So the problem of designing such such two source extractors was asked by two papers. One by Santa and Vazirani, and the other by Shore and Goldreich in mid-80s. And the paper by they showed that the inner product function is a two-source extractor where the sources are n comma 0.51 n min entropy. So x has min entropy at least 0.51 n, and so does y. And this was in. So subsequently, there was not much improvement on this problem of coming up with explicit two-source extractors. Then after 20 years, Burgin showed how to improve this in 2005, where each source has min entropy 0.5 minus a small universal constant. So this is a very tiny constant. It comes from some product theorems in additive combinatorics. So it remained, and also there was a subsequent work by Raz, who showed how to extract from n comma 0.51 n and so Raz showed how to extract when one of the sources have min entropy slightly larger than 0.5 n, and the other can have really small min entropy.
Many bits, right? Because for one bit,
yeah, for the one bits. Right. Yeah. Right. Yeah. Yeah. For one bit, it's a folklore result. The Paley, you can use the quadratic residue. Yeah. All right. So it remained a challenging open problem to come up with two source extractors for min entropy anything much less than 0.5 n.
So what is the parameters of this folklore result?
The folklore result is that so it's essentially this parameters, but it outputs just one bit. And there is a conjecture in number theory which actually says that it should work when both the sources have constant. So there is a conjecture that the proposed construction actually works for n comma delta n for any delta, but this is open in number theory. So
the matrix is a matrix of quadratic residues modular. So you have the field with p elements, let's say, on rows and columns. You write plus or minus 1, whether it's a quadratic residue or not. And if it's p by p, then it's directly, well, theorem. Every window, every set of rows and columns where, let's say, you have about root n rows and log n columns will be unbiased. Slightly more here, slightly more. That's not a simple calculation.
yeah, so this take the sum of the two sources and check if it's a quadratic. Okay, and so our main theorem is explicit two-source extractor for k greater than log power cn for some small constant c, which actually can be taken to be 75, and it has been further improved to 10 now by improving one of the components by Raghu Mecca. All right. Okay. So our proof can be on a very high level broken down into two parts. So the first part is using x. So we'll assume that the two independent sources are x and y. Right? So they are on n bits and they have min entropy at least k. So our first step is using x and y. So our first step is using the two independent sources x and y to get a non-oblivious, a q comma t non-oblivious bit fixing source on a polynomial number of bits, and I'll get into what this is. So this is, so okay, informally a bit fixing source is a source on n, say on, I'm overloading n, so on n bits, such that it has a set of coordinates where each bit is independent and uniform, and the other coordinates may arbitrarily depend or not depend upon these good bits. But this is some kind of a generalization of these sources, and most of our talk will actually be designing extractors for these sources, so I'll get into this slightly later. And let's call this source Z. Okay, so so if you call this as M, then Q is M power 1 minus.
I mean, what was the meaning of Q?
Oh, okay. Yeah, sorry. Okay. So Q represents the number of bad bits, and T represents actually that the uniform bits are not independent, but actually T-wise independent. Yeah. Okay. And our second step is designing and for short I'll write it as Q comma T non-oblivious bit fixing sources for a certain range of parameters of Q and T, which is exactly what we achieve in this step. Yeah, this is a deterministic extractor. Yeah, because we have already used both our sources, so we essentially forget that we have two independent sources. Now just work on this Z and extract one uniform bit. And subsequently, Lee actually showed how to get extractors for these sources which output more bits. So the focus of this talk will be part 2, where we'll assume that we have such a reduction, and then we'll extract from these sources. And if we have time, then we'll get into the details of how to get a bit fixing source from these independent sources. Okay, so I'll briefly mention that some ingredients in step 1 is some objects called as non-malleable extractors. So these non-malleable extractors, explicit constructions of non-malleable extractors were known for min entropy rate 0.5 n, and in a recent work that I had with Goel and Vipul Goel and Shinley, we managed to construct such extractors for, again, polylog min entropy. And this was crucial in achieving this reduction. So yeah, I'll get into details after going through step 2.
Eshan, can you write a little bigger? It will be more
Sure.
visible for
Yeah.
people here and to the camera.
Sure, yeah. All right.
Polylog mean entropy, and you want to say the parameters, say T and Q or so? So T is
There's also polylog.
T is also polylog, and Q would be, if the number of bits is say m, then Q is m power 1 minus delta. Yeah. And we design extractors which extract from such parameter ranges. Okay. So let's forget about step 1 and just focus on designing extractors for Q comma T NO non-oblivious bit fixing sources. And let's assume that I'm overloading n, and let's assume that the source is on n bits. Okay, so let's formally define what let's first define what oblivious bit fixing sources are. So an oblivious bit fixing source, say a Q oblivious bit fixing source, is of this form. So it's a string of length n, and there are a set of bad coordinates Q, and the size of Q is Q, and bits, and let Q bar be the complement set of Q. So bits in Q bar are uniform and independent, and it's oblivious if these bad bits do not even depend upon these good bits. So suppose we get us, is that clear? So
we can cure fix.
Yeah, the bits in Q are fixed. Yeah.
Yeah, so the difference between the two is when the adversary gets to choose the bits in Q.
Yeah.
In the oblivious case, it chooses the bits in Q before
Yeah, exactly.
the
Good
bits
bits are chosen.
lost, and in non-oblivious, it's after.
Exactly. Yeah. Right.
You could also call it function fixing, something like that. The bits are in Q are functions and depends on the bit on Q bar.
Yeah, in the non-oblivious case,
In the
yes.
non-oblivious.
Yeah. Right. Yeah. So, yeah. Let me reuse this, and a non-oblivious bit fixing sources are where, as we discussed, so bits in Q depend on bits in. So, for example, in the oblivious case, a very simple extractor is just to take the parity of the bits, because it's the good bits are the bad bits are fixed, so parity would work, right?
Even if you had just one.
Yeah, exactly. But in the case of non-oblivious bit fixing sources, the situation is not so easy, because clearly parity would not work, right? Because the adversary could choose always one of the bad bits such that the parity is fixed to 0, say.
It's even more serious than that. You are working with particular parameters where Q is small, but if you were working with Q is big, with the normal
Yeah.
range for extraction, even if you have half the entropy,
Right.
it's as hard as extracting from general sources.
Yeah.
It's impossible.
It's impossible. Yeah.
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 It's impossible to do deterministic.
Right. Yeah.
Right.
Yeah.
It's just that here it's very important that you have some linear.
Yeah. Exactly. Yeah. Yeah. As Avi pointed out, it's actually impossible to extract from such non-oblivious bit fixing sources for, say, one would try to say extract from by setting Q to be say 0.1n, but that's not possible by we'll get into why that's not possible. So, and let's now define what
So actually, there is no restriction about the bits in Q, right? You could have just written that the bits in Q bar are uniformly independent, and that's it. The fact that they depend somehow, it's like the most general thing.
right. Yeah. The special case I think is when they do not depend, and that's the oblivious. So yeah, you're right. Yeah. Okay. And Q comma T non-oblivious bit fixing sources are when the bits in Q bar are T-wise independent. So here we assume that the bits in Q bar are each individually independent and also uniform, but this places a weaker restriction on the good bits, that they're just T-wise independent. And in this talk, we should think of T as polylog in the polylog n.
Exactly, or you allow almost independent or something?
Yeah. So yeah, in our actual reduction, they are almost T-wise independent, but
Epsilon is very small.
yeah, our reduction we managed to get epsilon small, so that we can argue that it's close to some T-wise independent distribution. So there's a general lemma which says that if the distribution is T comma gamma wise independent, then it's close to some T-wise independent distribution where the statistical distance is gamma times n power T. So yeah.
Yeah, it's by no.
I'm sorry?
The theorem is by no.
Yeah. Okay. So, right. So the way to design extractors for such non-oblivious bit fixing sources is via a connection to resilient functions. So let's define what resilient functions are. Okay, so let f be a Boolean function. And let q subset of n, q be any subset of n, and what we want to define is the amount of influence that these set of coordinates have on this function f. All right. So all right. So also let the size of q be small q. So the way we define the influence of this subset on this function f is with respect to a distribution D is the number of the probability. Here, let me just formally state it. So so let's look at what this quantity means. This is the influence that the set Q has with respect to the distribution D on the function f. So this is the probability that if you sample the bits that are outside Q in Q bar, so we sample a string of size n minus q from this distribution D and set the bits which are outside Q to this string y, and then we look at if the function is already determined or not after this fixing. Right, so if it's not determined, then it sort of says that the coordinates in Q can still influence the outcome of the function. Right? And some special cases we'll look at are when D is the uniform distribution on n minus q bits, then we'll call this quantity just IQ. And when D is t-wise independent, we'll call this quantity I q comma t. Yeah, so yeah, that's the, and IQ comma D is defined to be the maximum over all subsets of size Q. So this quantity says the maximum influence that a set of size, a subset of coordinates of size q can have on this function f with respect to the distribution D. Right, so
Yeah, there's
Yeah.
always
So let me erase this. So I think I can erase the steps. Right? All right, and the lemma is to connect these functions which have low influences for any subsets to designing extractors for these non-oblivious bit fixing sources. So suppose f is a function such that is bounded by epsilon 1 . Suppose we have a function which has low influence for, there is a max over all device independent distributions, whose influence is bounded for some parameter q. And further, the function is almost balanced on any device independent distribution.
When you say balance, you mean qis on the entire n bits, right? Not
Yeah, this is not a partial evaluation. This is on n bits. Then f is an non-oblivious bit fixing sources. So this lemma, this is a simple lemma, and it connects the problem of designing extractors for non-oblivious bit fixing sources to coming up which are resilient under device independence and also is balanced under any device independent distribution.
You say resilient, you mean functions with low influence?
Yeah, it's resilient to coalitions of some size, right? I mean, let's look at a proof sketch of this. All right, so let x be q comma t non-oblivious bit fixing source, and let E be the event that f is, all right, so what this means is that, so x looks like this, right? It's a string on, it's a source on n bits, and there is a set of bad coordinates q, and the size of q is bounded by q, right? And the bits outside q are t-wise independent. So we'll look at, so yeah, the probability that we'll look at is, let's look at this event E when say x is sampled from x and the bits in q bar are fixed to say xq, where xq denotes the projection of x onto these xq bar, onto these q bar coordinates. And now suppose we evaluate, and all right, so what we are doing is sample a string x from the source x, which is a q comma t NOBF, and now look at the coordinates in x which are in q bar and set these coordinates to the corresponding string and partially evaluate f. And we look at the probability that E is the event that f is fixed on this partial evaluation, right? So since we know that f is f is resilient, so we know that this event happens with very high priority, right? So I mean, if you write out
just so
yeah,
all you're doing is just saying that when you sample x,
right,
if it happens that the assignment to q bar fixes a function,
right,
then you are balanced because
yeah,
you don't care about the bits outside.
exactly,
It's fixed already.
yeah,
It's whatever. It has a
yeah,
probability, equal probability of being one or
right,
1 or 0 up to epsilon 2.
yeah, exactly,
Right?
yeah,
You do that, and
yeah,
this is what you care about because the probability is not fixed. It's most epsilon.
at most epsilon,
It's
yeah,
just random.
yeah, yeah, yeah. So yeah, essentially that's the argument, that once f is fixed, then you could as well assume that the bad bits are coming from a t-wise independent distribution. So the guarantee that f is almost unbiased under any t-wise independent distribution says that the function under this fixing is unbiased up to this error epsilon 2, and we have an additive error of epsilon 1 because that's the probability that f is not fixed, right? So this is roughly the proof sketch, and what this says is that expected value of f of x minus half is at most epsilon 1 plus epsilon 2. Okay. The next step is to translate this. So now the task, so we initially began with the task of extracting from non-oblivious bit fixing sources. Now this has translated to coming up with such functions. Now we'll translate this into coming up with functions with slightly easier properties, or at least it looks to be easier. So think of q as n power 1 minus delta, like n power 0.99.
It's very important that it's bigger than the root, and you cannot get
Yeah.
too close there.
Okay, but if it's constant, it's like a simple example of a resilient function.
If n is
Q.
q is just a constant.
Yeah.
then majority, yeah.
Up
Yeah.
to root n.
Up to root n. So now what we show is that if this function also satisfies some other nice properties like being an AC0 circuit of low depth and is also a monotone function, then it's enough to bound the influence of the function, assuming that the good bits are actually uniform, and also showing that just the function is unbiased under the uniform distribution. So that seems to be an easier task. So more formally, again, suppose f is from n bits to 1 bit. Now suppose f is an AC0 of depth, of small depth d and size m, where think of both d and m as, so d as constant and m as poly in n. And further, f is monotone. F is an AC0, depth d, size m. And the influence of suppose the function f satisfies all these 4 properties. So the first property says that it's a small AC0 circuit. And the second property is that f is also monotone. And the third property says that f has bounded influence under the uniform distribution. And finally, f is balanced under the uniform distribution. Then for t greater than for some large enough constant c, actually the c that we get is, okay, so yeah, I'll get into the parameters later. So for t greater than log bar cn for some c, where d is any t-wise independent distribution on n bits. and think of epsilon 3 as a small inverse, so 1 by n power say 0.1, and this this affects this constant c. So it can be chosen to be any arbitrarily small polynomial, and that just blows up the c that we get.
The concept is also influenced by the depth d, right?
Exactly.
Like
Yeah.
in your case, it would be some specific.
Yeah. Actually, the bound that
The depth will be 4.
depth will be 4. Yeah. Yeah. And we use the bound by Avishay's result. Okay. So this essentially says that the function f now has slow influence under any t-wise independent distribution, and is also almost unbiased under any t-wise independent distribution. So since this says that exactly these are the properties that the lemma wants for a function to be an extractor for non-oblivious bit fixing sources, so it's enough to get a function which satisfies these 4 properties. Right, so let's look at a proof of this lemma now, and this theorem now. All right. So there are 2 observations which lead to this lemma, and the first is, let's forget that f is in AC0. Let's just use the property that it's a monotone function. Then the observation is that if f is monotone, it is easy to check if, say, by fq I mean the function where, so let y be a string in n minus q length string, and let fq be the function where f is partially evaluated with on the coordinates outside q. So it's easy to check.
It's actually not such a good. Maybe you want y in the subscript.
I see.
Right? It's not the value of f.
That's true.
F
Yeah.
is restricted to
Yeah.
y on q bar.
So right, thanks. If this function is fixed or is a constant function, and how do we do this? So all we can do is check if f q bar y of 0 bar is not equals to
1.
yeah it right. So yeah, actually okay, yeah, given the so okay, so since it's a monotone function, if the coordinates in q actually influence the function f, then the evaluation of f q bar y on by setting all the bits in q to 0, and by evaluating f q bar y with all the bits in q set to 1, have to be different if the bits are, if the coordinates in Q are influencing this function, right? Okay. Yeah, this is a simple observation, but so another result that we'll be using is a breakthrough result of Braverman in the area of pseudo-randomness.
So just a second, this
Yeah.
thing you just showed, this is used to say that the bias doesn't change. You will use it
Right.
in order to show that the bias doesn't change. Right?
Both the bias and
Both
the
the bias
and the influence. Yeah. 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 So the aim is to say that if if F is an AC0 circuit, then this thing can also be checked by a small depth AC0 circuit. And once we can do that, so there will be a circuit which evaluates to 1 only if it's not fixed. So the bias of that circuit essentially is the influence of the set of coordinates. So right. I see. So actually I think yeah. Yeah. Yeah, it's a different function, yeah. So I think the bias is derived from Braverman's result because F is an AC0 circuit. Right? Yeah. And this was recently refined by Avishai. So what this says is that if you have a circuit C, say, which outputs just 1 bit, and C is an AC0, depth of depth D and size M, and suppose T is greater than I think this the constants, some constant C times. Is this? Yeah. Then for any D on n bits, Ty is independent, the bias of C is preserved under the distribution T. So when X is sampled from the uniform distribution, when X is sampled from this T-wise independent distribution, is bounded by epsilon. Right. So now the idea is to use this observation and this breakthrough result in pseudo-randomness to actually say that if the influence of F is bounded under the uniform distribution, then the influence of F is also bounded under any T-wise independent distribution. So yeah, I could probably just do it here. So we had this function f q comma y bar, f q bar comma y, which is the evaluation of the coordinates outside q to y. And suppose we have this indicator function, again say which is from q bits to 1, which is a Boolean function, such that this evaluates to 1 if and only if f q bar comma y is not a constant function. Right? So it's easy to see that I q comma the influence that the q coordinates have on f is equal to the bias of this function. Probability that u q bar y of, say, where z is sampled from a uniform qubit string is equal to 1. Right? And now the observation is that this function is actually an AC0 circuit of depth d plus 1. And this is because of what we saw here, that the circuit E is essentially f q bar y set to 0 not equals to f q bar y with set to 1, right? And this can be computed with another additional depth.
So the monotonicity was for that, and it could have been that there would have been some other way
To check,
to
yeah.
check for some function.
Yeah, I mean, even if it's say unate, then we could check. But I mean, in general, it's a hard problem to. I mean, it's it's satisfied.
You can always check all the possible values, but
But then there's an exponential, yeah.
let's
Yeah.
go.
Yeah. So it's easy for this if it's monotone, but but then the size explodes for general. So now we use the property now we use the result of Braverman and Thal and say that the bias is roughly preserved when z is drawn from any t-wise independent distribution. And this translates into a bound on I q comma t of f. So what we have shown is that for any shown is that for any subset q of size q, the influence it has under the uniform distribution is also close to the influence it has on a t-wise independent distribution. So this lets us prove this result. And this directly follows from the fact that since f is in AC0, its bias under any t-wise independent distribution is close to its bias on the uniform distribution, which is epsilon 2. So we get this extra factor from the t-wise independent. Right?
So you use actually the result Braverman twice, one on
Yeah.
Q and one on Q bar.
Yeah, exactly. Yeah. Yeah, one on the directly on the function f and one on this slightly higher depth circuit. Yeah. Yeah. Okay. So I think the rest of the part of designing this extractor we can actually forget most of the things that we have done so far and just focus on coming up with such a function.
Eshan,
Yeah.
it's up to you, but we can take a 5 or 10 minute break.
Sure, yeah. I mean, it's up to you.
But usually we leave it to the speaker, but the speaker can ask the audience if they want.
Yeah, I mean, if the audience wants a yeah, I think 5 minutes maybe. Yeah. Okay.
Okay.
So to recap, we need a function. So the remaining task is a function which is low depth in AC0, monotone, has low influence under the uniform distribution, and is also unbiased under the uniform distribution. So if you have such a circuit, then this can be used. This is also an extractor for non-oblivious Q, T non-oblivious bit fixing sources. All right. So the starting point for constructing such a function is a construction by Ahatay-Lineal from 1990. So this is a probabilistic construction, and the naive de-randomization takes n power order n squared time. So, and also it's not monotone. So it's not direct how to use this function, and further.
I think it's an exaggeration, but it makes sense to the n squared. I mean, we have a good pseudo-random generator.
Yeah.
So,
Right.
so
Yeah.
no, it doesn't.
I mean, yeah.
We didn't have the
Right.
techniques,
Yeah.
but
Yeah.
Well, even constructing two-source extractor in this time is hard.
You can actually get it in this time.
Polylog entropy only.
Yeah, for polylog. Yeah, for 1 bit. Yeah. All right. So let's start out by defining these well-known functions called as tribe functions. So a tribe function can be visualized in this way, that you have a top OR gate, and we take ANDs on disjoint subsets of variables. So these variables correspond to tribes, and the function evaluates to 1 if there is unanimously a tribe which says 1, right? So the Ahatay-Lineal construction is of this form. It's okay. So let's set up some notations. Let n be m times b, where we think of this as the size of the tribes as b, and this is m. So the Ahatay-Lineal is a function with a top AND gate, and it does AND of a lot of tribes on the same set of variables. So let's define let p script p be a collection of partitions p1 through, say, pr, where each pi is a partition of n into blocks of size p, right? And let pij denote the jth block. Then the Ahatay-Lineal function with respect to, okay, so the Ahatay-Lineal construction is actually slightly more complicated. We also need a collection of functions g1 through gr, where each gi is a function from n to 0, 1. And the Ahatay-Lineal function with respect to this set of partitions and this set of functions g. So it's an AND of these tribes. So
To
Oh.
negate some variables.
yeah, just to negate some variables. So it's so this is the artilineal function with respect to this class of partitions P and the set of functions G.
In every partition, there has to be one set that agrees with G.
Yeah.
Yeah. And what they prove is that if you randomly choose your set of partitions and also randomly choose the set of negations, then with high probability, the functions in the sample space have low influence for Q as large as omega of n by log square n. So our contribution here is
And how do you set the parameters R, M, and P?
So it will be balanced at the end.
it will be balanced at the end. So
Close to log up to some log, right?
yeah. So you can think of the size of the blocks as log n minus log n. And R is, in the original construction, R is actually equal to n. Yeah. So our construction is a modification of the artilineal function, making it monotone and also explicitly constructing a collection of partitions such that the properties of influence and the bias is also preserved. So the first modification is to just remove the functions G. Yeah, I think that's pretty much the construction, except that each variable XL is also now a circuit on a disjoint set of variables. It's a CNF on a disjoint set of variables. And the only reason for that is now the size of these partitions are actually n power delta. So what we want to do is to make these XLs one with very high probability. So instead of analyzing the bias with respect to the uniform distribution, what we'll do is analyze the bias of this function with respect to the Bernoulli distribution, where each XL is one with high probability, very close to 1.
So you just make each XL will be an OR of some disjoint of.
Yeah, we'll make it an AND of ORs just to reduce the depth here. All right, so from now we'll assume that these XLs are, so this is the function and we are analyzing the influence as well as the bias of this function with respect to the Bernoulli distribution. Okay.
And the sizes of the blocks will change.
Yeah. So the size. So now we'll see how to explicitly construct such partitions.
Why do you need the XIs to be CNFs? Why can't you have them just...
No, it's just a thought experiment. We'll just forget about this. Just think
Yeah.
that he's allowed to pick XL as a Bernoulli variable, not half-half, but P1 and
But bias towards 1.
And then you will simulate it with another way.
Oh, so you don't want to take P half, you want to take
Yeah.
that.
Yeah, yeah. because in our explicit construction, the block sizes are large. So just to handle that, we have this extra thing. Okay. So the way we construct these partitions are in the following way. So before going into this, so the explicit constructions use some things called as seeded extractors. So we'll just use a graph theoretic way of viewing these things. So suppose this is the set of r bit strings, where think of r as 2 power r. So I'm using these variables in the same way so that we can relate easily to what's happening. So suppose we have a seeded extractor ext on r bits, which I could also state it as a collection of, but so such an extractor takes in a weak source x, uses a seed of length b, which is uniform, and outputs m bits. So another way of seeing this is saying that, and the property is that the output of the extractor is close to uniform. Sorry. Yeah. So, yeah. And this is a statistical distance as we define. Sorry. And x is, so if this extractor works for min entropy k, so this has parameters k comma epsilon. So it works for weak sources with min entropy k and has error epsilon. Okay. So this can be graph theoretically interpreted as you have this set of r length r strings, and the set is of size 2 power r. So and on this side we have the set of m bit strings, and this graph corresponds to the output of the extractor. So on input x, if there is a seed which takes you to output, say, some z, then there is an edge between this. Right? So this is a graph theoretic way of looking at this extractor.
The degrees are 2 to the b on there.
Yeah. The degrees is 2 power b, and think of all small letters as logarithms of the capital letters. So b is 2 power b and m is 2 power m. And this extractor satisfies a very nice property, which is so this is a theorem by Zuckerman in 97, which says that if you look at any t which is a subset of the output strings, and look at the number of neighbors, look at the x's which have significantly large intersection with t, like more than the density of t, then the number of such x's can be bounded. So define bad to be the set of x in r-bit strings such that by n of x, let's denote the neighborhood of x, intersection with t is, say, significantly larger than the density of t. So t is just the size of t by 2 power m plus epsilon times, so the size of each neighbor of x is 2 power b, so just using that notation. So what the theorem says is that the number of such bad x's is bounded by 2 power k, which let's denote by k. Is actually less than this. All right. So after this detour, let's get back to our construction. So our explicit construction of these R partitions. So each partition corresponds to an x on the left, which is an r-bit string. So let's take any x which is in 0, 1 power r. Now we define the set P say x 1 to be, so let the neighbors of x be, say, W1 through WB, right? So we'll define the first block of this partition as 1 comma W1 through 1 comma WB. And so corresponding to each x, we have an initial partition of the block. And to get other blocks of this partition, we just shift these WBs. So recall that each WI is an m-bit string, right? Because the neighborhood of x is m-bit strings. So say is defined to be 1 comma where the plus means maybe the bitwise XOR of interpreting j as an m-bit string. We shift each of these points by j.
It's not clear why it's a partition.
It's not a partition.
Yeah, it's not a partition. Yeah, sure. All right. So yeah, this is strictly not a partition, but there is an easy way of interpreting this as a partition in the following way that sorry. Yeah. So what you can think of this as a curve in 2 dimensions, and we are shifting. So what we have is sure, yeah. Oh, I see what. Oh, that's the yeah. Sorry. Yeah, yeah. Oh, I see. Yeah, yeah. It is a yeah yeah. Right, I see what the yeah it.
That's what you wanted. You want b times m.
Yeah, so n is b times m, and right. Yeah, I thought it's not a partition because you're saying it's an ordered tuple, but yeah, there's a natural bijection. So yeah, all right. So this will be our collection of partitions, and now let's try to argue some okay, I think I can remove this now. So I guess with this construction, we already have that this function is a monotone function, and it's also constant depth. So the remaining tasks are showing that it has bounded influence and also it's unbiased. So the easier of the two tasks is actually showing that the influence of any subset of size n power 1 minus delta is bounded. So let's first do that.
So you didn't pick the size b yet. So b will be n. You want to say that b is about n to the delta.
Yeah.
Top line.
Yeah.
This parameter.
Right. So yeah. So think of m as n power 1 minus, say, delta by 10, and the error of the extractor is anything less than delta over 4.
So R will be polynomial in n.
Right. Yeah. Yeah.
Capital R.
Capital R. Yeah. 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 So yeah, we'll crucially need that the error of the extractor is less than the delta that we are handling. Okay. So one part of the proof is bounding influence. So let's suppose we have a set Q, and we want to bound the influence of this set. So let's individually look at the influence of this set on one of the tribe functions. It's some variable x1 through xp and so on. So I haven't really talked about how biased these xi's are. So let's look at the proof to see how we set the bias.
I think X is overloaded.
It's too many x's. Let's maybe.
It's okay to be the variable.
Partition.
One x is. Oh, this x. Yeah. This,
Oh,
yeah.
I
This
see.
is problem. Yeah. Here you can use it. I know this. This is just a vertex in the
Yeah,
expander.
yeah.
Well,
Yeah, so maybe just
well,
let's change this to v maybe.
V like this, so it's even worse.
V is still worse.
The weirdest.
All right. Yeah, let's use x here. So we'll want that the probability that xi is 1 is 1 minus p1, where so there is a top AND gate with fan in R, an OR gate with fan in M, and the final AND gate has fan in B. So think of P1 as order 1 over B. So the probability that, say, one of the tribes, say x1 xi is from 1 through B is equal to 1 is 1 minus P1 power B. Let's set this to P2, and we would want P2 to be order 1 over M. It's 1, right? Because you're just multiplying. Yeah. And finally, so
P1 is 1 over P.
it's actually it's there'll be a log. Yeah. Yeah, there is a yeah, but these all are very small with comparison to tilde of it's even the constants need to be set very precisely. So okay, and let's call this function f. So and let this tribe function be, let the tribe functions be called as FIs. So and all these probabilities are over the Bernoulli distribution. So probability that Fi of x is equal to 0 is 1 minus P2 power M, and this is again, I think this is actually order 1 over R.
You want, for the final thing to be balanced.
Right, yeah. So what we'll aim for is these ORs, even though they are on the same set of variables, to somehow act independently. So I mean in some sort of independence. So if each of these are ones with probability 1 minus 1 over R, then we would expect 1 minus, say, ln log 2 over R, then we would expect this final thing to be unbiased. Okay, so with this setting of parameters, let's try to bound the influence of this set Q on this function. So the first observation is, so we'll try to bound the influence of Q on just this one of the tribes, right? So one of this entire tribe function. So the first observation is that
Just a question. Are you going to make it to show that this probability is much smaller than 1 over R? The probability that Q influences this part of the
right,
part.
yeah.
So then you'll use the union part.
Yeah.
Yeah. So here the fact that the partitions are interacting with each
No.
other wouldn't bother us.
Wouldn't bother, but
That's why this part is simple.
yeah. So this part uses just this property of the extractor that any subset has low intersection. So
The balance, to show that it's
To
balanced.
balance, this is the harder thing, but this is just to, you just
Yeah.
want to show that the
It has.
line under these probabilities is resilient.
yeah, exactly. Yeah. Yeah.
So this is a simple calculation.
Yeah, it's a yeah.
But you should decide if you want to do this calculation or to explain more how to do the balance.
I see. Okay.
See, well, you have 25 minutes.
All right. So yeah, let's quickly just see. Yeah, I mean the proof idea is what Avi just pointed out. So I mean the trivial way of bounding the the influence would just give you that the influence is at most 1 over R, and then if you take a union bound, it's not good enough. So what you want to say is that we can actually prove a stronger bound on the influence using the property that the partitions are from.
So you do, so it's not just a union bound. It will not
Yeah, it's a union bound after this stronger.
after, yeah, okay, that's cool. Yeah.
Yeah.
Good. Yeah.
Yeah. All right. Okay. So yeah. So to save time, let's assume that a simple calculation gives that the influence that Q has on any tribe is at most 1 over R, which is not very difficult to show. So let's now try to show that we can actually prove a stronger bound on the influence using the property that the partitions come from an extractor. So let's define what a bad partition is. So a bad partition,
To get 1 over R, it's even if they don't have, if the partitions do not satisfy any property.
yeah. Yeah, but it's not good enough for the union. Yeah. So a bad partition with respect to the set Q. So a bad partition is bad with respect to Q if it contains, so Pi is bad if there exists a block Pij such that this block has a significantly large intersection with
We actually expect this intersection size to be constant.
I mean,
In
yeah,
expectation.
in expect.
Expectation, because it's n to the delta over 10, and this is n to the 1 minus delta.
Right. So yeah, I mean if there is a significantly large intersection, then we say that the partition is bad. Now using the property of the extractor, what we can show is that there exists at most k times m bad partitions. And let's quickly try to argue why this is true. So k is 2 power k, where k is the min entropy of the seeded extractor, and m is 2 power m, where m is the size of the output.
Actually, what do you take to be k in this? I mean,
Yeah.
whatever you like.
Yeah, so k is picked to be delta r, delta prime r. So actually in our construction we take k to be 2 times delta r, 2 times delta small r, little r. Yeah,
So it's linear entropy.
it's
like
linear
the
entropy.
extract of all
Linear entropy. Yeah. Yeah. So it's crucial that k times m is little o of capital R. So, and this is
So this will use this Zuckerman.
yeah, yeah. And the proof is simple. It says that suppose there are at least these many partitions, then there exists, so we'll arrange them and then say that there exists a shift J such that there are at least m bad partitions corresponding to this. And that implies that a shift of the extractor is not an extractor, so this gives the bound that we want. So yeah, so one term of the union bound is this, and the second term comes from a stronger influence on this good part, on the partition which is good. And the idea there is the following. So let's look at this. Let's look when a set Q can have influence on a tribe's function.
It's all of its members vote 1, right?
Yeah. So yeah, and also we want to argue that what the outside members have to do for the set Q to still have some influence. So what we want is that all these AND functions which do not have a variable from Q, they should evaluate to 0, right? Because else this becomes already 1. So we want all these gates to be zeros which do not have a variable from Q, and we want at least one AND gate which has a variable from Q to be such that, suppose it has a variable say W which is from Q.
So that's 0 in it.
Yeah, and we want all the other things to evaluate to 1. I mean, if we want it to have influence.
If it were, yes, if there was a 0 there, if
Then we are,
if
yeah.
every one of these Km parts had a 0, you would be.
Yeah, so in a good partition, what we have is that in each block, there are at most 2 epsilon b entries from Q, right? And most of these are not from Q. So we want all of them to have 1, and that's a very low probability. So that's where we get a better influence. So yeah, and
It's like taking the same function but with
smaller blocks. Yeah, exactly. Yeah, right. Yeah, so yeah, I'll skip the calculation, but it's, so if this is little of, so this is little of r, so, and here we can actually take all of them, and we are proving a 1 over r times and actually it comes to be something like n power omega 1, so the influence of the function is bounded. And the next part is proving that let me just take out this part. Proving that this function is actually balanced.
But Km over R is big, right? It's not small enough.
It is, so we ensure that, so it's linear, sorry, yeah.
It takes the O of R such things.
R is,
Now it's polynomial.
Right.
so K is, so little k is 2 delta little r. So capital K is r power 2 delta. Yeah, yeah. So, right. And the way we bound the bias of this function is, so it's easy to evaluate the bias till here. So we know that the probability that each of the tribes evaluate to 0 is P3, which is small.
Yeah, these are independent.
These are independent. Now, let's in the event EI that Fi of x is 0. Then the probability that the final function f of x evaluates to 0 is we take an OR of all these. And now using the mutual exclusion inclusion principle, in particular the Bonferroni inequalities. So what we can say is that is the probability that f of x is 0 is bounded by the same summation and we think of lambda as r power a small constant delta. So, and where each So any SC looks like 1 is less than I1. Say J1 is. Right. So what we do is we prove a tight bound on probability of, say, any of these terms, even and through.
You want to compare it to the product.
Exactly.
The probability of P1 to the power C.
Yeah, 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 yeah. And this is where we use Jansen's inequality. So what we could think of is picking a set T, subset of N, where each element in T is picked with probability 1 minus P1. So this set T corresponds to the coordinates which are ones when the x is picked from a Bernoulli distribution. So the probability that E1 happens is that the probability that this tribe evaluates to 0, which implies that none of the tribes is contained in this set T, where the set T corresponds to the ones. Is this clear? So the probability that E1 happens, which is equal to probability that F1 of x, where x is from the Bernoulli distribution, Bernoulli n comma 1 minus P1 is 0, is equal to probability that for all, say, L in M, P1L is not contained in T. Right? And the probability that this happens is exactly equal to the probability that each of the tribes for all these partitions is not contained in the set T. Okay. So for all L in M, for all I in C, P I. Oh, I switched notation. It's not in T. And this is where we use the pairwise low intersection property of. So now we need a new property of the partitions, which is that if we look at any Pi1 J1 and Pi2 J2, then the size of this is bounded by 0.9 b, where so if we take any two partitions and look at any two blocks, then their intersection is bounded by some constant times this. So if this happens, then the Jansen's inequality can be directly used to show that this is approximately equal to the product of i's from 1 to c, a probability of ei. And plugging this in here and with some manipulations actually gives us that this behaves like independent tribes. So that's how we bound the bias of the function.
Some of the Janssen SET is to bound probabilities that many sets are contained in T, right? You want sets are not contained in T.
I think the version of Janssen that we use actually gives us probabilities of the set not contained in T. So it says that, sorry. Yeah, it's from the, I think it's from your book with. Oh, Yeah, maybe it's, yeah, I think it's lots of paper, like there are at least 3 papers which come up with slightly. So, I mean, if people are I could state the, if, yeah, that could be of interest. So, all right. The Jansen's inequality, the version that we use is of this form, that let omega be some set, and suppose we pick the set T, where each T is picked with, say, probability P, and let S1 through SR be subsets of omega, and define these quantities. So what we want to bound is the probability that for all I in R, Si is not contained in T. And we want to roughly say that this is equal to the product of so for this to hold, we need 2 conditions. So the first is that none of the sets are too large. So the probability of Si contained in T is bounded by some tau, and the quantity delta, which is probability Si is in T and Sj is in T for Si intersection Sj for all sets which have non-trivial intersection. This quantity is bounded. So if we call this as, say, some W, then the Jansen's inequality states that this probability P is one minus tau. So if we can show that delta is little of 1, then we have a very tight bound on P. And this condition that the blocks do not have too large an intersection translates into proving a bound for this quantity delta, because you are saying Si is in T where each is picked with probability 1 minus P1, right? So we are saying that at least 1.1 B elements are in your set, and that's where the gain comes from.